Hello, hi, welcome. Today's topic is going to be really interesting, mainly because I think it's something that basically no one has ever covered before, especially the autophagy people, the Dr. Fungs and Dr. Berg, and even the what I would consider more qualified fasting authorities. I don't think that any of those individuals have ever covered the mechanisms of autophagy the way that we're going to be covering them in this video. And the reason for that is because it's essentially what I'm trying to do in this video is answer a question that I think more people should be having is how does autophagy discriminate between the healthy components of your cells and the unhealthy components of your cells? Is it a mass murder? Is it just going to go in and just destroy every aspect of your cell? No, it's not. There's selection there. There's some form of selection. And if you've been with Physionic for quite some time, you know that cells don't think. They don't have brains. So if they can't think and autophagy is selective for particular unhealthy sections of the cell, how does that happen? How does the cell discriminate, in a manner of speaking, between the healthy and the unhealthy? Now, if you're not familiar with who I am, my name is Nicholas Verhoeven. I'm a PhD candidate in molecular medicine. I am a cell biology researcher, and actually some of my research is in autophagy. That's why, or that's one of the reasons why I'm covering this topic. Just last week, we covered how metabolism affects mitochondria, and this week, I wanted to cover this topic on autophagy. It's probably going to be a little bit shorter video than some of my other longer content, but no less scientific. So we're definitely going to be diving into a decent amount of molecular biology and cell biology, and hopefully I can fascinate you with how the cells are able to distinguish between the two, healthy and unhealthy. So let's jump straight into it from here on out. So the question that we're examining is, how does autophagy discriminate between healthy and unhealthy cell components? And this information is going to be coming from the paper, the review paper that I covered last week, but I left out certain sections because I wanted to leave them for this podcast episode. And I asked you guys if you were interested in me covering this particular topic, and I had a few responses saying yes. So I thought, why not go ahead and jump into it. So metabolic regulation of mitochondrial dynamics comes from the Journal of Cell Biology, which is a reputable journal. And then I actually ended up diving into, I didn't do a full deep dive like I did with this one. So this one you can actually you'll find all three of them attached to this content, but this one you'll actually find my notes, where I've got all my detailed notes breaking down some of the jargon so you hopefully have a better understanding of what this all says in the entire paper. But then we've got this one or these two studies that I ended up just briefly looking into as well to kind of make sure that I'm making good on the accuracy of the information that I'll be presenting to you today. The PINK1 Parkin pathway activity is regulated by degradation of PINK1 in the mitochondrial matrix. Don't worry, I'll be explaining some of that. And differential submitochondrial localization of PINK1 as a molecular switch for mediating distinct mitochondrial signaling pathways. Okay, so both of these are going to be important as we go forward. All right, so the question is in kind of a visual format. So I already presented it in a vocal and visual format in terms of text, but in this situation, I've got this format of, we've got what's known as a phagosome. So when we think of autophagy, what we're actually talking about is the degradation or the breakdown of usually large cellular components of the cell. There can be smaller proteins and things like that also get wrapped up in this vesicle, and that's what ultimately ends up creating this vesicle right here. But this phagosome ends up enveloping a mitochondrion. In this situation, it doesn't have to be a mitochondria. It can be any component of the cell, but I'm going to be focusing my discussion on mitochondrion because that's what I study in the lab. But a lot of these principles are going to apply to other components in different ways, but we're still going to get an answer to this overarching question. So the phagosome will come in here and envelop the mitochondrion, and then we'll end up fusing and through this process of autophagy, will then end up fusing with another vesicle known as the lysosome. And then we have the autolysosome from there, and then that lysosome is filled with enzymes and a really low pH, an acidic environment that ends up degrading and destroying everything that's inside, that's trapped inside of this phagosome. So that is generally how autophagy works. Now the question is, if we have a healthy mitochondrion here, why does the phagosome not take out this healthy mitochondrion, and yet it does take out this damaged or somehow non-functioning mitochondrion? And again, this could be a healthy component of the cell, an endoplasmic reticulum, a peroxisome, whatever you want to call it, and a unhealthy peroxisome or endoplasmic reticulum or whatever component. I'm just using mitochondria as our test subject. So it all starts, specifically when we're talking about mitochondrion, it all starts with this protein named pink, and that's why I've created this diagram where the protein is literally pink. So we're going to be following what this protein does, and this is going to be the key to the distinction between these two proteins, or these two mitochondria, excuse me. So one of the key aspects of healthy mitochondria, so here what we're looking at is healthy mitochondria. So right, we've got one mitochondrion, and we're zooming into this little section right here, and in this section there are two membranes. If I go back here, you've got your outer membrane, you've got your inner membrane right here. So here we've got our outer membrane and we've got our inner membrane, and we've got our intermembrane space, which is simply the space between the outer membrane and inner membrane, and we've got the mitochondrial matrix, which is this inside section of the mitochondrion, and outside is the cytoplasm, which is the rest of the cell. So we're all within a cell, but now we're moving inside of a single mitochondrion. And the outer membrane has these pores, or these transporter proteins, we'll call it that, transporter proteins that allow certain proteins into the inside of the mitochondrion. So we have some that are on the outer membrane and we have some that are on the inner membrane, and the proteins will then navigate their way through. They don't quite look like how I've got them diagrammed here, but we don't really care about that at the moment, or really at all for this discussion. The point is that proteins, certain proteins, can enter into the mitochondria and enter the very depths of the mitochondria known as the matrix. Now, why does that happen? How is that possible? This is in a healthy mitochondrion, and the reason for that is because of what's known as polarity. So there are two aspects that I've identified as healthy mitochondria. So these two aspects are, one, the damage that's been done to the mitochondrion. So if you have no damage or very little damage to the mitochondrial matrix, to the inner membrane, to the outer membrane, et cetera, then you have a healthy functioning mitochondrion, presumably. The second component is the polarity, or the membrane potential of the mitochondrion. So let's examine that. So there is a membrane potential that is found here that is relative to the outside of the mitochondrion. This is inside the cell, but outside of the mitochondrion. This is inside of the mitochondrion. And I've kind of denoted it here by adding 3 negative signs. So the point is here that there is a negative charge that is found inside the mitochondrion relative to the cell. So the cell is more positive than the mitochondrion. However, if you were to then measure the cell compared to the outside of the cell would be typically more negative than the outside of the cell. But in this comparison, we're just relative to the inside of the cell. So this is very negative by comparison to the cell. So this polarity, this difference between the more positive, that's the way I'm describing it, the more positive inside of the cell, although it is technically still negative, the more positive part of the inside of the cell, that polarity between the two leads to an attraction between certain proteins that fit through these pores, that fit through these transporters, these channels, in a manner of speaking, will then attract those proteins into the matrix. So they'll go from a more positive environment to a more negative environment. And that is due to this attraction between the difference between the two. So what happens to this pink protein is that pink is outside of the mitochondrion. It's getting closer to the mitochondria and eventually gets attracted and gets pulled through these pores, these transporters. And once it enters, what it does is it gets cleaved by another protein that is called LON, the LON protease. And there are a number of different proteases that do this, but LON is one of the big ones that have been identified as a protease, a protein that cuts up other proteins, to simplify that. So this protease will cut the pink protein and essentially make it less functional or make it non-functional. Now, why would it want to do that? Well, the reason is because pink, when it is active, when it is doing its function, it will actually lead to the degradation of components of the cell. So it is attracted to these, if you have a damaged mitochondrion, for example, or if you have a damaged component, if that's an endoplasmic reticulum or whatever, in this situation, pink is more specific to mitochondrion. The pink protein will go to the mitochondrion and will start phosphorylating it. And I'll show you a diagram of what that looks like in just a second. But it will add these tags to the mitochondrion, which will then make it kind of stick out like a sore thumb. So do we want that if the mitochondrion is healthy? No, we want to keep our functioning, healthy mitochondria. So in that situation, pink will be pulled into the mitochondrion and be degraded. That's one scenario. And this is a major scenario, but it is just one scenario. I'll describe a few others in other situations. So pink is a trigger for mitochondrial degradation. And in healthy mitochondria, we do not want to degrade healthy mitochondria. That makes sense. Now let's look at an unhealthy mitochondrion. So in this situation, the big difference here is if you look at the membrane potential, there's no polarity. There's no difference between the potential in here compared to outside of the mitochondria, still inside the cell. So they're more similar. They may not be exactly the same, but the point is that they are more similar to one another. As such, that means that pink is not attracted to the inside of the mitochondrion, and pink will stick outside of the mitochondrion. In such a case, it will then accumulate on the outer mitochondrial membrane right here. I only have one shown here, but you start having an accumulation of pink. This then leads to this phosphorylation event. So essentially it's adding a phosphate molecule to a series of different proteins. I don't have them all laid out here, but you essentially have a series of proteins that get these phosphate molecules that are attached to them. Now, as such, this then also recruits another protein known as parkin. This is, yes, indeed, if you've made the connection between Parkinson's and this protein parkin, these are closely related with one another. It is often believed, at least to a certain degree, that parkin is involved in Parkinson's disease. Now, but it also plays a role in just kind of normal physiological cell maintenance and autophagy, et cetera, et cetera. So it's not just Parkinson's disease. So parkin will come in here, and it is what is known as an E3 ubiquitin ligase, which means that it will take ubiquitin molecules and attach them to different components or different parts of the cell. In this situation, parkin is recruited to the mitochondrion, one because pink is starting to accumulate the mitochondrion because of this lack of this membrane potential, and then the parkin will start to attach ubiquitin molecules to all the different proteins that I do not have displayed on the membrane, but there are, we're talking thousands and thousands of proteins. They all start getting tagged with these chains of ubiquitin. Now, pink will further phosphorylate these ubiquitin chains, and that will then lead to a series of different ubiquitin chains all over the mitochondrion, along with pink, along with parkin. And this is then a distinguishing factor, if we then compare the two, of how the autophagosome is able to distinguish between an unhealthy component of the cell, in this case a mitochondrion, and a healthy component of the cell. Now, this is just one mechanism for mitochondria. Now, there are other situations. So let me actually explain this. So there are these two defining factors at this point, that you get a loss of this cell, the mitochondrial membrane potential. So here it's very negative compared to the cell, and here it's positive compared to the cell. So this is a loss of the membrane potential. Great. Okay, but on top of that, that leads to the accumulation of pink, that leads to the accumulation of parkin, which I don't have shown here, and you have an accumulation of these ubiquitin chains that start to accumulate all over the outside of the mitochondrion. As a result, the autophagosome will then recognize that through a series of different proteins that are found within the autophagosome that I do not have displayed, and they will then envelop this mitochondrion and go through degradation through the lysosome, and then you have autophagy. And thereby, because there are no ubiquitin chains and no pink that's aggregating on the healthy mitochondrion, you do not have this autophagosome then attaching to the mitochondrion. So this is how we get selection in a biochemical sense without thought. There's no thought that's involved here. This is all biochemistry that's occurring inside the cell, which is leading to this discrimination between the unhealthy components of the cell and the healthy components of the cell. So now, before I jump to the conclusions here, I want to also point out that there are other mechanisms for this. So other mechanisms for pink, for example, you can get other control of pink, so it's not just degraded through these proteases that are found within the matrix, like the LON protease, and that's LON, not LAWN, LON. And on top of that, you can also get it cleaved by a protein named PARL, which is kind of like a really crappy version of French, parler, or parlay when we're talking about like pirates. This is PARL, just PARL, which is found, I believe, on the inner membrane, and pink will partly kind of like stick its butt in here, and then PARL will come in and slice off its ass. So, and then that leads to an inactivation of pink, because then pink is released, and pink will then be degraded by what's known as the proteasome. So this is another mechanism to control pink. And then finally, another mechanism, there are other mechanisms as well, but I just want to throw in a few others. Another mechanism is through nitrosylation of pink. So a tag will be added to pink, a nitrogen, I believe. Yes, a nitrogen will be added to pink, which will then inhibit it from enacting its role through the degradation of the mitochondria in this situation. So there are a number of different ways that we can control that our cells end up controlling pink, but I just wanted to highlight this one because it gives you a good visual of if you have a dysfunction that leads to a loss of this cell membrane, or of this membrane potential, then this then leads to a cascading event of pink, phosphorylation, ubiquitination, parkin, and then the eventual recruitment of this phagosome. Okay, so let me finish this off here, and we will just blast through these conclusions. For anybody that wanted to skip everything, you will have skipped all of the details. I don't even know why I have these conclusions, but there's always an uptick in people that just want quick answers, and unfortunately, I have to provide them. So here we are. Components of the cell are held in a homeostasis, and if that homeostasis is disturbed, that leads to a cascade of biochemical events, not the cell thinking for itself, that lead to those disruptors specifically being eliminated. For example, mitochondria must maintain a certain polarity, a negativity compared to the rest of the cell. If it becomes more positive, the biochemical processes that depend on the mitochondrial negativity will be disrupted, causing them to act differently from normal, thereby switching them to a destructive path wherein they promote the elimination of just those mitochondria that are more positive, leaving the negative charged mitochondria to keep functioning normally. Okay, well, if you've got questions about this, feel free to comment below. I'd be happy to engage with you. However, my only stipulation is please have watched the entire video. Don't ask me questions of how does pink get into the mitochondria? It's covered. Please just watch it. And then, but then of course I'd be happy if you have other questions that go beyond what I've covered. Certainly let me know, and I'd be happy to answer if I see your comment. All right, with that, thanks for stopping by, and I'll catch you in the next one. See ya.